Am I audible? Guys, are you alive?
Yes, sir, you are audible.
Okay, let me share my screen. My screen visible?
Yes, sir, it's visible.
Okay, so let us continue our discussion on operating systems. Today we will discuss about virtual memory management. So in the previous classes, we studied operating systems briefly. We studied data structures. Then we continued our discussion on operating systems, how a process management will happen, how a process will create its process using fork system call, then how uh, process is deleted using exit system call, and how the CPU will schedule different processes. What are the various issues in process management? We also studied after that the memory management. What are the various issues? How a memory will allocate various ways like best fit, first fit, and worst fit. When it causes defragmentation, fragmentation will happen. External fragmentation and internal fragmentation will happen. And we also studied that how we can overcome the external fragmentation and compaction. That's where we started studying paging. The paging will help you to eliminate the external fragmentation, but there will be some internal fragmentation. But the paging will help you to create page tables, and a page that is generated by the CPU address will be mapped by memory management unit to the logical address, physical address, which we call that as the frames. So from pages that is generated by logical address, it will map to the frames that is in the physical address using a page table entry that we studied in the previous class. So paging is one memory management technique where the memory management will happen very efficiently. Now, let us continue our discussion on virtual memory management. So we'll try to study virtual memory management today. But before that, if you recall, in the beginning of the class, we discussed one thing, and I'll repeat the same question. So let me ask you this, and you guys tell me what do you think. Suppose your RAM size in your system or laptop is only 2 GB. Okay, your RAM size is only 2 GB, and you want to watch a movie, say of the size 5 GB or 10 GB, more than your RAM size. Suppose if your file, the movie file uh, memory space that will take is like say that 5 GB. Your RAM is only 2 GB. Will your computer can play that movie? Is it possible to play that movie? Will the movie will be played in your computer with 2 GB RAM playing 5 GB file? Is it possible? Come on, think and tell me. What is your thoughts? You are having a RAM of 2 GB. Your file is having 5 GB. Will your computer play that movie?
Yes,
Yes,
sir.
sir, due to virtual memory location, it will play.
Good. So even though your file size is more than your memory, still because of this virtual memory management, that will execute. Your program will execute. Your file, you can watch the movie. What happens is that whatever the space that is available in the memory, that will be executed first, then the rest of the part will store in secondary memory. Okay, so the idea is like this. So you have a hard disk, right? We have hard disk. This we call that as a secondary storage. Whenever you are using a file or playing a file, this file from the storage, it will be brought into RAM. This is RAM, is also called as primary memory. This is also called secondary storage and primary memory. This is called secondary storage or secondary memory. This is called primary memory. From primary memory, the CPU will execute its instructions. Maybe to mismatch the speed, there might be cache in between or registers, but ideally, CPU will take the instructions from RAM. So, suppose you have 5 GB data and your RAM size is only 2 GB, and then in this 2 GB also, some space will be occupied by operating system. So, out of this 5 GB, only the parts of that first movie part, say 1 GB, that will be brought here. Only part of a file will be loaded into the RAM, then that will be executed by the processor. Then after finishing the second part, whenever the movies keep on playing, the rest of the part will be swapped. It will bring it again to the RAM, then whatever the movie played, that will be stored back into the secondary storage. So here the process, it will take hectic. Ideally, so far what we studied, whenever a program need to be executed, it should be available in the RAM. That's how we have managed, we handle the memory management. This should be, whenever a process is need to be executed, that should be there in the RAM. Now the question comes whether the complete process should be loaded or only the part of the process should be loaded. So if only part of the process need to be loaded because of limitations of RAM and many other factors, we can go for virtual memory management. This virtual memory management will help us, even though your file size is large, still you will be able to execute. So virtual memory is a technique that allows the execution of a process that is not completely in memory. One major advantage of this scheme is the programs can be larger than the physical memory. Virtual memory abstracts the main memory into external large uniform array of storage, separating the logical memory viewed by the programmer from the physical memory. Programmer may assume that you have only 2 GB, how you will play 5 GB. That is, no need to worry. Programmer no need to worry. Programmer will see that the computer will have the 5 GB memory only. Logically, he will see that the computer will has 5 GB memory and it will work. Okay, so this technique frees programmers from the concerns of the memory storage limitations. So you don't need to worry about memory storage limitations because virtual memory will be taking care, even though your file size is very large than the RAM size, still you will be able to execute that code. And this could happen. Okay, so virtual memory also allows shared files, libraries to implement the shared memory. So but it is not easy to implement. However, if you choose carelessly the method, then it may cause substantially decrease in the performance. We should be very careful when we are choosing going for virtual memory. It is not that easy to implement. If you choose little bit carelessly.
Implement the virtual memory in our PC. Can you
Yes,
describe that? What was the basic operation?
come again. There was some question. Can you repeat your question? Hello. Am I voice? Am I audible, guys?
Yes, sir, you're audible.
Yes,
Somebody
sir, you're
was
audible.
somebody was saying something, right? Okay, fine. So this is the idea of virtual memory, but how we will implement? Uh, without decreasing the performance. How we will implement, we will see in the upcoming slides. So for the time being, a programmer would no longer need to be constrained by the amount of physical memory that is available. Users able to write programs for extremely large virtual address space, simplifying the programming task. Because each program uh, will take less, could take less physical memory, more programs could be run at the same time. So only part of the programs will be brought into the memory. In that way, more programs can execute, which will increase the CPU utilization and throughput. But because many processes are running in the memory, it will need to be continuously swapping, and that causes you increase in response time and turnaround time. That will cause you increase. Although it is increasing in CPU utilization throughput, response time, turnaround time will not increase. So it will decrease. Okay. So less input output would be needed to load or swap portions of the programs into the memory when each program would run faster. So you can see here virtual memory, which is larger than the physical memory. In the previous class, when we studied paging, paging is a memory technique that we studied, right? So we have pages, which is generated by logical address, but you see that you have frames. Frame size is the physical frames are the physical memory, which is very bigger. Usually physical memory will be usually bigger than page table. We have pages, we have page table. This page will go to this reference, this page will go to this reference, something like that, right? There is a page table reference, we have pages. But you see here in virtual memory, the page size is bigger, the physical memory size is smaller. Still you'll be able to do that. The memory map will happen in a such a way that you'll be able to we'll be able to handle the virtual memory even though your file size is very big. Your program may bigger size than your physical memory, then appropriate when your program, when it converts into process, they will be, when CPU generates the logical address, then they will be allocated those pages, only those pages will be loaded, rest of the things will be swapped. We will try to understand that how that will work. Okay, so virtual memory involves separation of logical memory perceived by the developers from physical memory. So developers will think that because it is 5 GB file is executing, your computer is capable of executing the 5 GB, so it hides, it separates the logical memory perceived by the developers from the physical memory, because physical memory is 2 GB, but you are logically executing 5 GB, so it involves a separation. So this separation is extremely large virtual memory to be provided for the programmers and smaller physical memory which is available. Okay, so that is the main thing. So let us now try to understand one concept before discussing the actual virtual memory, which is virtual address space. Now, in your C program, uh, you created a program called, let us say that I'll write one program. You tell me what is this program is. Suppose I'm writing a factorial of a given number in a function. I'm writing factorial, and you can verify the condition if n not equal to 0 or n greater than or equal to 1. Till this condition is true, we can call the function fact of n minus 1 multiplied by n. Else return, you can write return 0 or 1. Sorry, else return 1. What is this program called? When a function is calling itself, what is this called?
Recursion.
Recursion,
Right.
sir.
Recursion, right? Whenever you're calling a function by itself, it's called recursion. So what happens when you call recursion functions? This function n is called n minus 1 times. This fact again will go, it will call itself. It will keep calling. Where this function will store? When they are calling itself, where this function calls will be stored?
Sir, in stacks,
Right. So they
in
will
RAM.
store in stack. Okay, they will store in stack. Whenever you're calling a function after function itself, those function calls will be stored temporarily in stack, and stack will execute those recursion functions. Okay, you heard about dynamic memory allocation, malloc, calloc.
Yes, sir.
What is the data structure that is used by dynamic memory allocation? Anyone explode? When you are allocating dynamically memory, what is the data structure behind the dynamic memory allocation which is used?
The pointer.
Heap. Heap is the data structure that is used. Explore that. Okay. For dynamic
Yes,
memory
sir.
allocation, heap is the data structure that is used. Or dynamically linking libraries when you are executing. Suppose you include stdio.h. That is a library that need to be loaded at the time of execution. Otherwise, printf scanf functions won't work. How do you link those libraries? Using heap. They are dynamically linked libraries. Anyway, so the virtual address space of a process refers to the logical view of a process stored in the memory. Typically, the process begins at the central logical address, say 0 to max. So some text and data will be stored here, and a large blank hole space is stored. We can see that which is stored between stack and heap. So heap data is stored here, stack is stored here. Whenever a recursion call used, the stack memory space is used. Whenever dynamically memory allocated, the heap memory space is used. So stack will come from top to bottom, heap will go from bottom to top. Okay, so the large gap between heap and stack is a part of virtual address space that will require the actual physical pages if the stack or heap grows. You can see that this virtual address space includes the holes known as sparse address spaces. Using this sparse address space, which is beneficial because the hole can be filled as a stack or a heap segments grow if you wish dynamically link the libraries during the program execution. During when a program is executed, this dynamically linked libraries will grow. Either if you are using a heap, it will grow from bottom to top. Either it will grow from stack, it will grow from top to bottom. When you're using a program execution, if your memory is not having sufficient space, then this virtual address space is used to execute your program. Still, your program will be executed. So let us now try to understand the demand paging, how the virtual memory works. So when you are executing a program, which will be loaded initially from secondary storage into memory, right? That's what we studied in the first time. So you have hard disk. From the hard disk, you will store to RAM. From RAM, it will store to processor. This is how usually CPU. Usually it will happen. So executable program might be loaded from secondary storage to into memory. So this will has to come from here to here. When you are doing that, one option is load the entire program into the physical memory into the execution. Alternative strategy is load pages only when they are needed. Okay, instead of loading the entire program, load only which are needed. So if you load an entire program in the physical memory, what happens? So this may create a problem loading an entire program, because with this approach we may not initially need the entire program in the memory. Loading an entire program in the memory, loading the entire executable code for all options, regardless whether that option is ultimately selected by the user or not. User will choose that option or not, we don't know, but still we are loading the entire program because that program need to be executed. So that is one way. Other way is you load only the program which are needed, okay, based on the demand. So this is needed, you say that this is demanded, then you load that page only. So the alternative strategy to load pages only when they are needed is called demand paging, which is commonly used in virtual memory systems. Okay, so demand paging is used in virtual memory management systems, loaded only when they are needed. So with demand virtual memory, pages are loaded only when demanded during the program execution. Pages that are never accessed are thus never loaded. Which are never accessed will never load into the physical memory. Demand paging system is similar to a paging system with swapping where the process reside in secondary memory. I already told that the virtual memory looks like there is actually physical memory, but it is stored in secondary memory. Every time some space in the main memory and the file stored in the second memory will be keep swapping from main memory to uh, secondary memory. So demand paging system is like paging system is swapping where process reside in the secondary memory. So demand paging explains one of the primary benefits of virtual memory. By loading only the portions of programs that are needed, uh, so memory is used here more efficiently. So we will try to understand how this will work. So you understood paging. We have logical memory, we have physical memory, we have page table. So when we are storing this pages into the frame, we will store only the needed pages. For example, for the time now only A, C, F are the needed pages. So we will store only A, C, F. Rest of all the process A to H are stored in the secondary memory, space. Now, which process need to be stored in the memory? Which page need to be stored in the memory? Which page should not will be decided by a paging mechanism. The same paging how we discussed in the main memory. The same paging technique is used, but with an additional parameter called valid and invalid bit. Okay, valid and invalid bit. Suppose okay, let me explain this. So the general concept of demand paging is to load the page in the memory only when it is needed. As a result, when a process is executing, some pages will be in memory, some will be in secondary storage. So you see this A, C, F are only in the memory, but D, G, H, E all in the secondary memory. So some part of the pages will be in the memory, some part will be in the secondary memory. Thus, we need some hardware support to distinguish between these two. So, which is stored in main memory, which is stored in second memory, we need to understand. For that, we will create an additional bit in the page table called valid and invalid bit. If it is a valid bit, then that page is stored in the memory. If it is an invalid bit, that bit is stored in the secondary storage. Okay, is this clear?
Yes, sir.
So the valid and invalid bit schema can be used. When bit is set to valid, then that associated page is both legal and in the memory. If the bit is set invalid, the page is either not valid or is valid but is currently in the secondary storage. That is not logical address of the space of the process. So using this valid and invalid bit, only the pages that are needed will be allocated the frames. Rest of the things will be stored in secondary storage. Now let us say that D is another process that is needed now. D is the process now it is needed. Now D can be you can see here A is the page 0. Page 0 is stored in frame 4. Frame 4 A is stored. It's a valid bit. B is not needed now, so it is kept invalid. It is kept in the secondary storage. B is not allocated. C, page 2, C6, it's valid bit. We kept in the frame 6. You go to frame 6, you will find C. D, it's an invalid bit, so it is not kept in the frame. We will kept here. E, again, it's an invalid bit, which is not kept. F, page 5, F is kept in frame 9. Frame 9, page F is kept. It's a valid bit. So remaining are invalid bit, like that. Now, suppose D is need to be brought into the physical memory. Now, what will happen? Suppose if there are another frame free available, when there is a free frame available, then D, the bit will be reset to valid. This will be reset to valid. D will be brought here. Suppose here, then the frame number, say this is 11. Okay, so the 11th frame D will be allocated. Okay, now suppose after that let us bring H. Now H wants to come. Suppose let us say that this all memory space is occupied. There is no free space. All memory space is occupied. Now another H wants to come. H wants to come. Then what we will do is there is no space available. Now what we will do is we have to replace either one of these pages. Either we need to replace A or C or F or D. When we are replacing that, suppose let us say that A need to be replaced. When we are replacing that, A will be brought into the memory first, into the secondary storage. Then this H frame 7 will be made this valid frame. This will be made, the bit will be made valid. Then the H will be stored, the frame number is allocated 4. Okay, so the 4, then H will be replacing 4. Okay, this will be deleted. Again, this will become invalid. This will become invalid. Is this clear?
Yes, sir.
So H will be brought here. So when a process is needed, that page only will be loaded into the memory. The remaining pages will not loaded into the memory. And when others are needed, if memory is available, frame is available, we will allocate it. If it is not, we will swap with the other pages. Which page we will swap? Why A? Why not C? Why not F? Why not D? Again, there are different strategies. Which is a victim? Here A is a victim in the example I told, but there could be other victims. C can be replaced, F can be replaced, D can be replaced. We can replace any page. There we will discuss page replacement algorithms. Okay, there are various strategies. Which page should be replaced? We will discuss in the upcoming slides. Page replacement algorithms. We will discuss that. Okay, if time permits, we'll discuss at least one algorithm today. So demand page, what happens? Now see, whenever you are allocating a page into the memory, when there is no need to swap, then there is no page fault. Whenever there is a swapping happens, now A is replaced by H. Okay, H is needed now. H is needed. It will search the page table. H is not there, and it will search in the secondary storage. H is there. When you are searching initially in the memory, H is not there. Later, you observe that it is there in the secondary memory. You swapped with A, brought this H in place of A, and you started showing that now it is available. Whenever a process for a page, when it is searching in the memory and it is not there, or whenever there is a bit which is invalid, whenever there is a bit is invalid, whenever that particular page is not available in the memory, we call that as a page fault. Okay, we call that as a page fault. Page fault occurs because that page is not in the memory. Ideally, the program should be loaded into the memory. Whenever there is a requirement, it should go and refer the frame. But when operating system is doing that, when the CPU is doing that, now there is no frame there, so it creates a page fault. The page fault is not there. Then whenever there is a page fault happens, so it swaps the memory from the secondary storage. So our goal is to decrease the page fault. The page fault should decrease as much as low. Whenever the page fault increases, then the system performance will decrease. Is this clear? You want me to repeat it?
Yes, sir.
Shall I repeat?
Yes, sir. One time, please.
See, here H is there, right? H wants to execute. CPU tells that I want to execute H. This is demanded. Okay. this demand will come, but it will search here. Initially, H is not there in the memory, right? Initially, A, C, F only were there.
Yes, sir.
Imagine this is the process, okay? Now, this is the valid bits. A, C, F are the only process available. Now, let us say that H is needed. H is needed. H is there in the memory or not?
Sir, in physical memory, it is not there.
It is not there. What about page table?
No, sir.
H is 7, page number 7. Page number 7 shows that it is an invalid bit, right?
Yes, sir.
Because this is not stored in the main memory. This is called page fault. Okay. So ideally this is a process. A to H, everything should be in the memory. Ideally what should happen? A to H, everything should be in the memory. Correct?
Yes, sir.
Then H should allot one frame. That frame should be accessed by the operating system. But here what we are doing demand paging. Demand paging says that allocate only the process which are needed. Which is not needed, don't worry about that. Whenever it is needed, you load it. So now H is needed, but if you observe this page table, H is not there. So that is a page fault.
Yes,
Okay.
sir.
That page table, that information is not available, right? H is not
Yes, sir.
available in the memory. Now, and we will see that page table, this bit is also invalid. So when such scenario happens, we call that as a page fault. Okay, so that's what I explained here. When a process tries to access a page that was not brought into the memory, then access to a page marked invalid causes a page fault because that page is not there. Ideally, it should be loaded, but we are not loading it. So that is page fault. Whenever page fault occurs, we need to replace that. Like how I told that page replacement algorithm, whenever that page is not there, we need to bring it back to the memory. So H, if the frame is available, if H, the frame is free, it will allocate that particular frame. If frame is not available, then it can replace any existing frames, ACF, any existing frames it can replace. Okay, is this clear?
Yes, sir.
So if the frame is available, then it will allocate that particular frame. If frame is not available, then it will replace any ACF. So that happens, that is page replacement algorithm. Whenever page fault occurs, we will go for page replacement algorithms. Okay, so the paging hardware translating the address to the page table, notice that invalid bit is set, causing a trap to the operating system. This trap is the result of the operating system failure to bring the desired page into the memory. So like this. So whenever a process is need to be loaded, that reference will be searched in the page table and it will observe that the page is invalid. Then trap is generated. Okay, the hardware will generate a causing a trap to the operating system. The trap will go to the operating system. The operating system will see that this particular page is available in the secondary storage backing up store. It will go pages on the backing store. It will verify. If it is there, it will bring to the frame. If it is free frame is available, it will bring that missing page. After allocating, it will reset the page table, make this invalid bit to valid, and the frame number it will allocate which frame it is allocated, then restart the instruction. Okay, whenever a page fault happens, operating system handles like this. Does this make sense?
Yes, sir.
I repeat it. So whenever there is a frame is invalid, the trap will make the operating system to look into the backing store. If that frame is available, it will brought into the frame, then reset the page table, make it invalid to valid, then restart the instruction. Okay. So these are the 6 steps I explained here. The 6 steps. We will check the internal table for the process to determine whether it is a valid or invalid. That is step 1. Step 2, if the reference is invalid, we'll terminate the process. If it is valid, and we will page it in. Okay. Then the third step is it will go to the free frame, schedule the secondary storage, decide the page into the newly allocated frame. When the secondary storage is complete, modify the internet table, update the reset table, modify the table to keep the process and indicate the page is now available. Restart the instruction. Sixth step, restart the instruction which is interrupted by the trap. The process now accesses the table which is always had in the memory. Okay. Now page replacement happens in the following approach. If there is no free frame, then we have to find which is not currently being used it, and we have to free it. If we can free a frame by writing it contents to a swap space, that is secondary memory, changing the page table, then indicating that page is no longer in the memory. So when you are changing this table bit, whenever you are changing, this need to be valid, right? In this case, when you are bringing H, this invalid should change to valid. Now suppose this process is swapping, suppose H is replacing in A, then this should become invalid. Is this clear? You should
Yes, sir.
change the valid and invalid bit appropriately. So likewise, if once we free the frame, writing its consent into the swap space. Now A will go back into the secondary space. Then we have to make that space change the page table indicating that page is no longer in the memory. Okay, so we modify the page table service using this. Find the location of the desired page on the secondary storage. Find a free frame. If there is a free frame, use it. If there is no free frame, use page replacement algorithm to select a victim frame. Write the victim frame secondary storage. Change the page and frame tables accordingly. Read the desired page into the newly freed frame. Change the page and frame tables. Continue the process where the page fault occurred. That's what we are discussing now. Is this clear?
Yes, sir.
So something like this. The process will look, PC will look into the logical process of process 1. B, the bit is invalid, which is means it will go and check the secondary memory. Once the secondary memory B is there, it will come and need to be replaced into the secondary space. I mean like the physical memory. Now, if the space is not available, then it has to replace either one of this approach, either one of this page. Then what will happen? This page will go, suppose it is replacing C will be gone here, then C bit will be invalid, this will become valid, in C place will go to B, then this become 3. Okay, that's how the need for the page replacement happens. So suppose there is another process, say that there is a frame 7 E, that is valid bit process 2. So then there is no problem, we can continue with this execution. So whenever there is a not required valid or invalid bit, we will observe that. Okay, is this clear? Likewise, G is there. If this bit need to be allocated, then we will replace any one valid or invalid bit. Is this clear? Page replacement, how it happens?
Yes, sir.
Now simple. That's what we explain by step by step. Step 1, page out the victim page. Now in this example that I discussed, initially A was there. A will be stored here. Step 2, change that invalid. Now A page should be made into invalid. Step 3, you bring that H into the desired page. A will be replacing by H into the frame. This frame, make it into valid bit. Fourth stage, reset the table and allocate the frame number here. So this is how the page replacement algorithm happens. Is this clear?
Yes, sir.
Okay. Now there are various page replacement algorithms. We will discuss one algorithm today because already we are running out of time. We will discuss the Fifo page replacement. We will discuss the rest of the things in the next class. So the simplest page replacement algorithm is first in, first out Fifo algorithm. So FIFO algorithm is like how we deal with the queue. Okay, associates with each page the time when the page was brought into the memory. So a page must be replaced, which is the oldest page is chosen. We will create a FIFO queue, hold all the pages in the memory. The head of the queue will replace the page which is the head of the queue, that is the front of the queue. We will delete the queue in the front, we will delete the head of the queue, and whenever a page is brought in the memory, we will insert at the tail. For example, let us see this example. Suppose this is the reference string. Initially this is the data pages. Okay, we need to different pages. These are the frames, frame 1, frame 2, frame 3. Okay, these pages need to be brought into the frames. Now these pages say 7, it is not there, we will bring into the main memory, which is freely available. Space is there, we will allocate it. When 0 is there, the space is available, we'll allocate it. So initially the front will point here, so we will allocate 7 here. Next, after allocating 7, front will move here, so we'll allocate 0 here. Then front will move to third place. After inserting, front will move, then 1 will be inserted here. Then after inserting, front will move to the next, right? Now front will move to the next place. Now 701 is inserted, 2 will come. 2 is not there in this list. There is no free frame. So 2 will be coming into the frame, replacing 7. So 7 will be replaced by 2. Then front will move here. After replacing, 2 will be replaced, front will move here. 0 will come, 0 is already there in the frame, no need of replacement. 3 will come, 3 will be replaced in the front. See, front is pointing at 0, 3 will be replaced at front, front will move to the next location. Next value is 0, 0 is coming, 0 will be replaced at the front location, front will move to the next position. 4 will come, 4 will be replaced at the front, then front will move to the next location. 2 will come, 2 will be replaced in the front will move to the next location. After 2 will be replaced by 3 will be replaced by 2. Next 3 will come, 3 is not there in the frame, so 0 will be replaced by 3. So 3 will come here, front will move to top again. Now the next element is 3. 3 will come, 3 is already there here, so no page replacement. 2 will come, 2 is already there, no page replacement. 1 will come, 1 just a second. So after inserting 0, this front will go to next position. Okay, the front will, after inserting 0, the front will go to next position. Next 1 will be inserted, replacing 2, front will go to the next position. Next 2 will come, 2 will be replacing 3. Next front will go to the next position. 0 will come, already there. 1 will come, is already there. 7 will come, 7 will be pointing at the front location, 7 will be replaced. Then front will go to the next location. Next element is 0. 0 will be replaced by 1. Front will go to the next location. 1 will be replaced by 2. Okay, sorry, 2 will be replaced by 1. Is this clear how it happens?
Yes, sir.
So FIFO is like first in, first out. Whichever comes first, that will be out first. So with this reference string, whenever we are making a table, that we call that is a page fault. Whenever you are replacing an item, whenever you are bringing a data from secondary memory to the frame, that we call that is a page fault. That's what we studied, right?
Yes, sir.
Whenever you are bringing a page from secondary memory to the primary memory, that is a page fault. So how many page faults here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 page faults. Total 15 page faults happen. Here there is no page fault because 3 is already there. Here also there is no page fault because 2 is already there. Okay, so the number of page fault happens like this. With the reference string, the number of pages, reference string and the frames, we will address the Fifo page replacement like this. Is this clear? You want me to repeat this idea? Anyone want me to repeat how this Fifo replacement example works? Okay, you have reference string 7, you will put the free space, 0 will put free space, 1 will put free space, 7 is the last inserted, first front will be pointing here only, it will be replaced by 2, next will be replaced, 0 will come, 0 is already there, 0 need to be replaced by 3, next it will be replaced 1, right? So 0 will be replaced by 1, next will replace is 2, 4 will be replaced by 2, next it will be replaced 3, 2 will be replaced by 3, next it will replace 0, 3 will be replaced by 0, next it will replace 4, 4 will be replaced by 0, next 3 should become but is already there, 2 should come, it is already there, 1 should come, it will be replacing 2, 2 will come, that will replacing 3, next 0 will come which is already there, 1 will come which is already there, 7 will come which is be replacing 0, and 0 will be replacing 1, 1 will be replacing 2. So total 15 page faults. Okay, so that's how it happens. Like the simplest page replacement algorithm, first in, first out. So when replacement algorithm, with each time when the brought into the memory, a page fault occurs. When a page is replaced, the oldest page is chosen. We create FIFO queue holding all the pages in the memory. We replace the head of the queue and we will insert at the tail. Okay. So in this example, I discussed that 701 causes page faults because they are empty frames. They are brought into the memory. The next reference 2 replaces 7 because 7 was brought into the first. 0 is replaced the next frame. 0 is already in the memory. We have no fault. And the first reference 3 is results in replacement of 0 since this is now in the first in the line. So because of this page replacement, we will continue this total 15 page replacements algorithm faults altogether. The Fifo page replacement algorithm is easy to understand and program. However, the performance is always not good. On one hand, page replaced initial model used a long time ago, which is no longer needed. On the other hand, because it is long time used, the variable what we declared, which might be in a constant use, then if it is replacing, we have to keep it, bring it on every time. So bad replacement choice increases the page fault, slows the process execution. Otherwise, it will cause an incorrect execution. We need to be very careful when we are making a correct choice or bad choice when we are replacing an algorithm. So let us try to observe with this example, then we will stop. Okay. To illustrate the problem with the FIFO replacement algorithm, consider the following reference. Now let us assume that we have only one frame. Okay, you have only one frame and you are bringing page every time. So initially 1 you will bring, next 2 will be bringing, but there is no free space, you will put 2 here replacing 1, again 3 will come, you will replace 2 by 3, 4 will come, again you will replace 4, this value will be replaced by 4, again 1 will come, so 4 will be replaced by 1, then again 2 will come, 1 will be replaced by 2, next 5 will come, 2 will be replaced by 5, next again 1 will come, so 1 will be replaced by 5 again, 2 will come, 2 will replacing 1, 3 will come, 3 will replace 2, 4 will come, 4 will replace 3, 5 will come, 5 will replace 4. How many total page faults happen here?
12.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if there is one frame, the number of page faults are 12, correct? This is number of frames,
Yes, sir.
number of page faults. So let us take 2 frames now. Let us take 2 frames. we have 2 frames. So initially 1 will allocate, next 1 and 2 will allocate, next 3 will come, 3 will be replaced by 1 because that is the last front will be here only. So 3 will be deleted by 1. So next friend will point here, next 4 will come, 3 and 4. Next 1 will come, 1 will be replacing 3. Next 2 will come, 2 will replace 4. Next 5 will come, 5 will replace 1. Next 1 will come, again 1 will replace 2. Next 2 will come, 2 will replace 5. Next 3 will come, 3 will replace 1. Next 4 will come, 4 will replace 2. Next 5 will come, 5 will replace 3. Is this correct? How many page faults happen now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So for 2 frames also, the number of page faults is 12. Now let us increase 3 frames. Now let us discuss with 3 frames. Now we have 3 frames. 1 will allocate. 2 will allocate. Now 3 frames. 1, 2, 3 will allocate. Now 4 will come. 4 will replace 1. 4 will be replacing 1, 2, 3. 1 will come. 1 will be replacing 2, 4, 1, 3. Next 2 will come. 2 is not there in the frame. So again 2 will be replacing 4, 1, 2. Next 5 will come. 5 will be replacing 4, 5, 1, 2. After 5, 1 is coming, 1 is already there. 2 is coming, already 2 is there. There is no replacement. 3 is coming. So 3 will replace 5, right? Sorry, 3 will replace 1. 3 will replace 1. Next 4 will come. 4 will replace 2, right? 4 will replace 2. How many page faults? Next 5 will come. 5 is already there. 1, 2, 3, 4, 5, 6, 7, 8, 9. For 3 number of frames, total page faults are 9. Correct?
Yes, sir.
So let us discuss now with 4 frames. So what happens when 4 frames? Let me delete this. So what happens when you take 4 frames? So for initially 1, 2, 3, you have 4 page faults. Is this clear? For
Yes, sir.
initializing 1, 2, 3, 4, you have 4 page faults. 1, 2, 3, 4, up to this 4 page faults. Next 1 will come. So there is no replacement required. 2 will come. There is no replacement required. 5 will come. 5 will be replacing 1. So 5, 2, 3, 4, right? 5 is done. 1 will come. 1 will be replacing 2. 5, 1, 2, 4. Next 2 will come. 2 will be replacing 3. 5, 1, 2, 4. Next item is 3. 3 will replace 4. 5, 1, 2, 3. Next is 4. 4 is replacing 5. 4, 1, 2, 3. Next element is 5. 5 is replacing 1. 4, 5, 2, 3. How many page faults? 4, 5, 6, 7, 8, 9, 10, 11. Is it correct? Sorry, up to this is 4. Up to this is 4. This should be 5. 5, 6, 7, 8, 9, 10. So total 10 page faults. Is that correct?
Sir, in this second column, 3 should be replaced by 5 now.
See, 1, 2, 3, 4. This is having 4 page faults. Okay.
Yes, sir.
Front will be in the here only, na? Front will be here. Front will be in here only. Next one will come. 1 is already there. 2 will
Then
come. 2
front
is
will
already
move.
there.
Front
No, front
won't
will
move.
not move. Rear will move. Tail will move.
Okay.
Front will be pointing at the first. Unless you delete an item, then only front will move.
Okay.
You delete an element in the queue, then only the front will move. We are not deleting so far, right?
Yes, sir.
So 2 will come. 2 is already there. 5 will come. 5 is not there. Then you have to delete whichever pointing front. So 1 will be replaced by 5. Okay.
Okay,
Next
sir.
element is 1 will now front will point here. Front will move here now because this element is deleted. Now 1 will come. 1 will be replacing 2. Right. So front will move again here. Next 2 will come. 2 is not there in this list, so it will insert at the front. Front will move again here. 3 will come. 3 will be replacing 4. Then front will move again here. Okay. Next 4 will come. 4 is not there here, so it will replacing 5. 5 will be replaced by 4. Front will move again here. Next 5 will come. 5 is not there, so it will be here. The total number of page faults are till up to this point 4, 5, 6, 7, 8, 9, 10. So 10 faults. Number of frames 4, 10 faults. Okay.
Yes, sir.
Now, ideally, if the number of pages are there and number of frame size, when you are increasing the frame size, what does that mean? You can accommodate more number of pages, right? When you're increasing the frame size, you can accommodate more number of pages. Is that correct?
Yes, sir.
Now, when you're doing that, see, frame 1 is giving 12, frame 2 is also giving 12, frame 3 came down to 9. But when you're increasing the frame size, this number of page faults should decrease. But it is increasing here. From again, it came to 10. Right? So instead of decreasing here, it increased here. Then again it is decreasing. So for some page replacement algorithms, the page fault rate may increase as the number of allocated frame increases. Okay? For some page replacement algorithm, even though you're increasing the number of frames, the page fault increasing. This is called Bellidy's anomaly. Okay? This is called Bellidy's anomaly. For any page replacement algorithm, the page fault rate increases as the number of allocated frame increases. We call that as a Bellidy's anomaly. So this Bellidy's anomaly is the biggest drawback of Fifo replacement algorithm. Okay, so bad replacement choice may increase the page fault rate and slows the process execution. So Fifo exhibits Bellidy's anomaly. Is this clear? Is this clear what I'm saying? As the number of frames increasing,
Yes, sir.
your page fault should decrease. But it is increasing here. You see, this is increasing here. This is called Bellidy's anomaly. Fifo execute. This allocation we did using Fifo only. Because we allocated using Fifo, this executed Bellidy's anomaly. So this is a bad idea. Okay, so that's why Fifo is is a bad performance. Okay, it is easy to understand, but however, performance is not always good. This is the biggest drawback of FIFO. So we'll discuss other replacement, page replacement algorithms. We finished FIFO. We'll discuss optimal LRU counting, all these algorithms in the Thursday's class. So we'll stop here. If you have any doubts, you can ask. Otherwise, we'll meet on Thursday. Any questions? Okay, no questions. Okay, I'll upload the slide. Please check whether you'll be able to see the slide or not. Lecture 24 virtual management. Can you see lecture 24 slide virtual management? Verify that. Verify the. Is it visible? Okay, nobody is responding. So please check that I already uploaded the slide.